Hello, my name is Kyle, and this is our Capstone project implementing digital twins for leakage detection in water pipe networks. Here's what we will be outlining in this presentation. So Melbourne is Australia's fastest growing city, and a rising population means higher water usage. In 2006, the Age newspaper reported that 39,668 million litres of water was wasted due to leakages. To locate these leakages, current methods include manual testing, tracer gas detection, and thermal imaging. Our main objectives in this report will include identifying the most efficient leak detection / pipe failure methods, identifying appropriate sensors and locations to gather live data, and recreating the pipe system using digital twins for monitoring purposes. And we will explore the following: responding to pipe failures and what methods we will use to record and analyze data, understanding how factors such as water pressure and water flow rate act within the pipe and how it can affect the life cycle of a pipe, what type of data is needed to create a hydraulic model, and can historical data be used in models to simulate a functional model, and what algorithm exists or needs to be developed to detect water pipe failures or leakages using a hydraulic model.
Hello, my name is Douglas. Here is a basic water network in Bentley WaterGEMS. We have a reservoir or tank that feeds the network. Next, we need to add in the initial head level, which represents the water available. Next is adding in pipe details such as length, diameter, material, pressure, etc., followed by installing junctions and sensors, which help naming and locating pipes and detecting leakage. Next, we add in structures such as valves and hydrants, followed with water meter data per house. Next is running the output model with the provided live SCADA data. This outputs water pressure, velocity, the hydraulic grey line, and head loss. From these results, we can analyze the outputted graphs, which shows the comparisons between the network functioning without leakage and with leakage, if there is any. Initially, we engaged the water authorities so we could have access to their water network data. The data received was all historical. In addition to this, we were given our case study location, Vermont South, finally followed with receiving all raw GIS data, which included pipe info, junctions, sensors, water meters, elevations, and much more that will be fed into the model. This will prepare the model for live SCADA data implementation at a future date.
Hi, my name is Yusuf Abba, and I will go through the case study of Vermont South and WaterGEMS hydraulic model. Background. The team was able, with Dr. Mushtaba's help, to reach out Yarra Valley Water Authority. Fortunately, Yarra Valley Water agreed to provide a case study of the purpose of this research. Yarra Valley advised that there are already IoT sensors installed in Vermont South, which is one of their water network. Conditions. After a board research on the water network of Vermont South, the conditions of this network are the following. According to the GIS and Dial Before You Dig website, most of the water network was constructed between the year of 1972 to 1973, and few sections were renovated during the years. The pipe material was used at that time was cast iron cement lined pipes. Size of these pipes vary from 40 millimeters to 225 millimeters in diameter. Small sizes for the customer distribution and large sizes for the transmission lines. In conclusion, knowing the age of Vermont South water network is 40 years old and the most material used was cast iron cement line pipe indicates that there is a great chance of the water leakages within the network due to the material used and the failure mechanism. Rusting and aging will be the most causes of the leakages in this network. As mentioned earlier, there are three components in digital twin: hydraulic model, live data, and digital twin, which is a combination of the two components above. Data preparation. After we received the data from Yarra Valley Water, about 6 gigabytes of raw Excel sheets, pressure, flow values, and shape files, we were able to access the data using the shape files, and we could read the information of the water network, such as material, length, and size of the pipes. 1. Building WaterGEMS model. Using the model builder, which is a function in WaterGEMS, we were able to produce a water pipe and junctions of VERMONT South Water Network in WaterGEMS. The pipes in WaterGEMS included all the information of the network, such as pipe sizes, material, age, length, and elevation. Water usage patterns and reservoirs. Adding water usage patterns is an essential step to build the hydraulic model. The importance of this step is to compare the typical patterns provided by the Water Authority to the real usage patterns provided by the IoT sensors when the demand is low. And this will result in two curves on the graph that will show the difference between the typical and the real usage of the water. Reservoir. For any water network, there must be a reservoir source of water to feed the network with the required water for the customers. Customer meter connection. We used Yarra Valley Water customer meter connection to create the demand for the hydraulic model through the load builder tool in WaterGEMS. This step is important to produce the water demand to be used for the hydraulic analysis in the coming stages. Model validation check. Using the validation option in WaterGEMS, the program will run a check over the existing model and check if there's any errors. After a few attempts and repairs, results were successful by producing a comprehensive hydraulic model in WaterGEMS.
Hi, my name is Christopher Marroquin, and today I'll be talking about the DRAWIN Collaborator. The DRAWIN Collaborator is one of the many functions that Bentley OpenFlows WaterGEMS software has to offer. This function is what will allow us to determine whether we have a leakage and the location of the leakage. It is important to use SCADA data, which is live data. This can be obtained from water authorities such as Yarra Valley Water in our case. Historical data, unfortunately, will not work with the DRAWIN Collaborator. Once having all the data necessary to run the DRAWIN Collaborator, the collaborator will compute all the data together, creating a solution that detects the leakage and also generates a graph displaying the current losses of water. Capstone team was successful in creating a functional hydraulic model. With multiple communication constraints due to COVID-19 proved to be difficult. Although the Capstone team made all efforts to complete this project, it was quite difficult learning a whole new program with minimal experience. These are the results of the hydraulic model: data preparation, building the WaterGEMS model, water usage patterns, reservoir, customer meter connection, model validation check, and the DRAWIN Collaborator.
Recommendations for the future groups. Maintain prompt replies to all external parties. This is where time can be wasted the most. All group members are urged to study WaterGEMS so everyone shares the same knowledge. Asking questions is also important. Industry partners want to help students and upcoming researchers and engineers. At the end of the day, this will help them more than us. An extra weekly meeting without your supervisor will help keep the group on track and shows initiative. As for future works for the continuation of this program, next steps are to receive live data from Yarra Valley Water for the case study, implementing the live data, analyzing results with Bentley to determine if these are true readings, report back to Yarra Valley Water, and then engage in a site visit to the suspected leakage area. Next is confirm the leakage on site, and then report findings.
But furthermore, implementing digital twins can detect the exact location of leakages and pipe failures in any water network. The team have created a fully functioning and comprehensive hydraulic model using WaterGEMS, and the next step is to acquire live data for the DRAWIN Calibrator. However, due to time constraints, the next Capstone team can move forward with this step, whilst maintaining the points of contact with Yarra Valley Water and Bentley, as it will be beneficial for the next team. Finally, we'd like to thank Yarra Valley Water and Bentley for this opportunity. Thank you all for listening to our presentation.